Welcome dear students once again into the class of topology, and we'll continue with more theorems, more concepts or more definitions on filters. So let us start with the new theorem on filters. The statement of the theorem says that let F be a map from a topological space X to another topological space Y, and there are two parts of this theorem. First part says that if B is a filter base on X, then the collection C of subsets FB of Y, where B is a member of the filter base B, is a filter base on Y. This is the first part of the theorem. And the second part says that if C is a filter base on Y such that every member of C intersects Fx, then the collection F inverse C of those subsets F inverse C such that C is a subset of C is a filter base on X. So we'll prove both these parts one by one. So let us start with the first part. Here we are given that B is a filter base on X. This is given to us, and we have to show that this collection C FB, where B belongs to B, is also a filter base on Y. So what we have to do, we will have to prove two things. Firstly, it does not contain phi, and secondly, if two sets are there, then there exists a third set in this collection which is a subset of the intersection of the earlier two sets. So let us see what happens for the proof of the first part. Proof of the first part: B belongs to B, and B is a filter base. So this means this B cannot be empty set. It cannot be phi, because filter base does not contain phi. And since B is not phi, that means f of B can also not be phi. And f of B is a member of C, and every member of C is non-empty, means phi does not belong to C. So the first part is very clear, very trivial. Let's move on to the second one. Let take two sets here. Let FB1, FB2 be two members of C. Then what these B1, B2 are? They are the members of the filter base B. Then B1 and B2 are the members of B, and B is the filter base. If B1 and B2 are members of B and B is a filter base, then there exists another B3 in B such that this B3 is a subset of B1 intersection B2, using the property of B being a filter base. Applying F on both sides, you get F of B3 is a subset of F of B1 intersection B2. But we know that F of A intersection B is a subset of FA intersection FB. So it is further subset of F of B1 intersection F of B2. So what happens? We have taken two sets FB1 and FB2 from C, and there exists another set FB3 in C, because B3 is a member of B, so FB3 belongs to C, obviously. So there exists FB3 in C such that FB3 is a subset of intersection of the earlier taken two members of C. So that satisfies the second condition for this collection C to be a filter base. So that means C is a filter base. Now we'll move on to the proof of the second part of this theorem. In the second part of the theorem, we are given that C is a filter base this time on Y. Earlier B was a filter base on X, and now C is a filter base on Y, and we are to show that this F inverse C is also a filter base on X. So firstly we will have to prove that F inverse C cannot be phi. To prove for the first part that F inverse C is not phi. Supposing on the contrary, if F inverse C is phi, what happens? If F inverse C is phi, then either C is phi or C intersection with F of X is phi. And both these are not true, because C is a member of this filter base, and in a filter base there is no empty set, so C cannot be phi. One thing is clear. And C intersection Fx is equal to phi means C does not intersect Fx, whereas it is given that every member of C intersects Fx. So neither this is true nor this is true, and this is a contradiction, and this is a contradiction because we have supposed that F inverse C is phi. So that means F inverse C cannot be phi, and this means phi does not belong to the collection F inverse C. Sorry, not C. Phi does not belong to the collection F inverse C. So first property for F inverse C to be for being a filter base is being proved, and now we'll move on to prove the second one. We will take two members of F inverse C and we will show that their intersection contains another member of the set F inverse C. Let F inverse C, F inverse D be two members of F inverse the collection C. Now what these C and D are? This means this C and D are the members of C. But C is a filter base on Y, so there must exist another set E in the collection C such that E is a subset of C intersection D. And taking F inverse on both sides, F inverse E is a subset of F inverse C intersection D. And we know that F inverse C intersection D is nothing but F inverse C intersection F inverse D. Also, this E is a member of C, and E is a member of C means F inverse E is a member of F inverse C. So there exists F inverse E in F inverse C such that F inverse C E is contained in intersection of F inverse C and F inverse D, and that proves the second part for F inverse C being a filter base on X. So it proves that F inverse C is a filter base on X. So this was the first theorem of this video, and now we will define ultrafilter and ultrafilter base, and then we will move on to the theorems based on ultrafilter base and ultrafilter and ultrafilter base. So let us see what an ultrafilter is. Ultrafilter is a filter which is not properly contained in any other filter on the same set. So let F be a filter on X, then F is said to be ultrafilter on X if two conditions are satisfied. Number one, F is not contained in any other filter on X, and secondly, if F star is also such a filter such a filter containing all filters of that kind, then F is contained in F star. That means simply you can say it is an upper bound, and moreover it is the least upper bound. So it is the definition of ultrafilter if it is not contained in any other filter, and then any ultrafilter is generated by some base, and that base will be called ultrafilter base. And now we will move on to the theorem. Theorem says every filter on a non-empty set X is contained in an ultrafilter on X. Every filter on a non-empty set X is contained in an ultrafilter on X. This is the theorem, and let us move on to the proof. Let X be a non-empty set and let F be a filter on X. Let C be the collection of all those filters F star that contain the filter F. Then one thing is obviously C is a partially ordered set. Let D be a linearly ordered subset of this C. Linearly ordered means if you take two members F1 and F2 from D, then either F1 is contained in F2 or F2 is contained in F1. This is the basic definition of linearly ordered set. So this I have just written here to tell you what a linearly ordered subset is. So we have taken D to be a linearly ordered subset of E. Now define E to be union of F alpha, where F alpha belongs to D. That means we have taken the union of all members of this linearly ordered subset D of the partially ordered set C. And we will show that this E is a filter. Claim E is a filter. And that is very trivial, very easy to prove. We have to prove three conditions. So first condition, phi does not belong to E. What is E? E is the union of all F alphas. These all F alphas are filters. And we know that no filter can contain phi. So these all alpha, in all these F alphas there is no phi. If phi is not in any of the F alpha, then how it can be in their union? So it is clear that phi is not a member of E. So first condition is clear. Let's move on to the second to prove that E is a filter. Secondly, let F belongs to E and H contains F. We have to show that H also belongs to E. Now F belongs to E. And what is E? E is the union of these filters. So if F belongs to E, then F belongs to this union. And if F belongs to the union, then F definitely belongs to some of the member of this collection. So this means F belongs to F alpha for some F alpha belonging to D. Now F belongs to F alpha. F alpha is a member of D and all the members of D are filters, so that means F alpha is a filter. So F belongs to this filter and H is a superset of F. So definitely if alpha is a filter, then if you take any member of the filter, all the supersets of that member must also be the member of F alpha. So this means H belongs to F alpha as F alpha is a filter. Now H belongs to F alpha, so definitely if F belongs to F alpha, then H belongs to their union also. So this means H belongs to union of all F alpha belonging to D, and which is nothing but E. So what we have shown, that if F belongs to E and H is a superset of F, then H also belongs to E. And this is the second condition to prove that E is a filter. Let us see the third condition now. In the third one, we will take two members of E. Let F1, F2 be two members of E. Once again, E is the union of these. So definitely F1 belongs to some alpha, F2 belongs to some F beta. So this means F1 belongs to F alpha, F2 belongs to F beta for some F alpha, F beta belonging to D. Now F alpha and F beta are the members of D and D is linearly ordered. That means either F alpha is contained in F beta or F beta is contained in F alpha. Without loss of generality, let F beta be contained in F alpha. Now F2 is a member of F beta and F beta is a subset of F alpha. That means F2 also belongs to F alpha. F1 already belonged to F alpha. So this means now F1 as well as F2 belong to F alpha. And if you have taken the other case, that means F alpha is subset of F beta, then F1 and F2 must belong to F beta in that case. And when both F1 and F2 are the members of F alpha, where F alpha is a filter, so F1 intersection F2 also belongs to F alpha. So this means F1 intersection F2 belongs to F alpha, and this F alpha is a member of D. So if F1 and intersection F2 belong to F alpha, definitely it will belong to union of alpha where F alpha belong to D, and this is nothing but E. So if you take two F1 and F2 from E, then F1 intersection F2 also belong to E. So this is also proved. That means E is a filter. Now E is not only a filter, but it is an upper bound of D. As E is an upper bound of D, as every linearly ordered subset of a partially ordered set has an upper bound. And since E is the union of all members of D, definitely E is an upper bound. So E is an upper bound of D. Therefore, by Zohn's lemma, C must contain a maximal element. C must contain a maximal element, and maximal element of C. All the members of C are filters, so this maximal element will also be a filter, and since it is maximal, it will become ultrafilter, which is an ultrafilter, and since all the members of C contain F, so that ultrafilter must also contain F. So which is there by Zohn's lemma, C must contain a maximal element, which is an ultrafilter containing containing the filter F, and that is the proof of this theorem. With this theorem, I'm going to close this video here. In the next video, we'll have more theorems, more concepts. Till then, thank you once again.